Hello everyone, this is Jingyu. I would like to introduce you my summer project at Georgia Tech University with Dr. Tabawada's group. My name is Jingyu and I'm from Agnes Scott College. So this is a preliminary explanation of the IceCube sensitivity within 2 weeks of neutrino transients. For those of you who may not be familiar with those backgrounds of particle physics, let me first briefly explain the terms. So what are neutrinos? They are neutrally charged subatomic particles with a mass close to zero and rarely interact with the normal matters. So some scientists call them the ghost particles and the most tiny quantity of reality ever imagined by human beings, since they are really hard to detect. So we have studied that there are three kinds of neutrinos, or three flavors: the electron neutrinos, the muon neutrinos, and the tau neutrinos. Each of the flavor can exchange to one another in a very complicated process called neutrino oscillation. Neutrinos are produced in high-energy collisions as they travel at the speed of light. There are many mysteries of neutrinos, such as their mass, the flavors, and oscillations. So now you may be wondering why we study neutrinos. Well, this is because studying them can potentially help us better understand many cosmic mysteries, such as the matter-antimatter asymmetry problem, what is dark matter, as well as the beyond standard model in particle physics. Among many mysteries of the neutrinos, one of the biggest questions is, where do they come from? What we know today is that a majority of those neutrinos zooming through space were born around 15 billion years ago, soon after the birth of the universe. As the universe continuously expands and cools, the neutrino constitutes cosmic neutrino background radiation. Other neutrinos come from general atmospheric phenomena as well as from the birth, collisions, and death of the stars. Here we are interested in neutrinos that come from the astrophysical objects, such as blazar, gamma ray bursts, and supernova. Another aspect of why we are studying neutrino astrophysics is because neutrino astronomy is part of the multi-messenger astrophysics spectrum. The messengers to study the universe include the photons, cosmic rays, neutrinos, gravitational waves, and more. At a wavelength where it is opaque to light or photons, it's still transparent to neutrinos, so that we can still use the cosmic neutrino flux as the messenger to reveal an unobstructed view of the universe. IceCube Neutrino Observatory, and this is the left picture, is that observatory located in the South Pole, is a cubic kilometer particle detector made of the Antarctic ice and located near the South Pole to study neutrinos. So the main detector is called the Digital Optical Modules, or DOM. So IceCube consists of 5,160 digital optical modules, or DOMs, each with a 10-inch photomultiplier tube and associated electronics to detect light. All those DOMs are buried underneath the surface of the ice and extend to a depth of around 2,500 meters. So this left picture is one of the DOMs that I just talked about. It is a sphere-shaped detector and there are in total more than 5,000 of them underneath the ice. So IceCube detects the high-energy neutrinos using something called Cherenkov light produced by the relativistic charged particles, which results from the interactions of neutrinos with ice. Cherenkov radiation is an electromagnetic radiation emitted when a charged particle passes through the medium faster than the light travels through the same medium, kind of like the supersonic aircraft. The sign of the Cherenkov radiation is a blue cone. So when the high-energy neutrinos interacts with the ice in Antarctica, the interaction produces a high-energy muon cutting through the ice, and the energy loss of the muon is captured by the dome of IceCube and creates the blue cone patterns you see on the right. Those are domes, and this is a blue cone Cherenkov radiation during that process. And so this is how IceCube works. So after introducing all of those backgrounds, my summer research project focuses on using a Python-based software package called FIRESONG to simulate neutrino populations. The story is like this. Although the IceCube observatory has discovered an all-sky diffuse flux of astrophysical neutrinos, the numbers and properties of individual neutrino sources still remain a mystery. My research goal is to use FIRESONG software to simulate different neutrino sources scenarios in the universe. The significance of my research is to help IceCube understanding better different scenarios of individual transient neutrino sources in the universe. This right picture is one of the plots I generated using specific parameter settings, such as the evolution, the time scale, and also as well as the density of the neutrinos. So the plot shows us the neutrino flux versus the number of neutrino sources. It's a histogram plot which shows us the distribution of neutrino fluxes on Earth. And this one is just showing you it's a Python-based language. It's just coding. So back to the title of my project, which is called Exploring the Sensitivity of IceCube to Less than 2 Weeks Neutrino Transient. So the reason I have this title is because my project goal is to find out the probability of observing an individual neutrino point source for a given source distribution. In other words, is to explore the sensitivity of the IceCube observatory. Neutrino transient means a non-steady source of neutrinos, such as a gamma-ray burst or supernovae. They are violent astrophysical events that produce neutrinos. The parameter settings we have here are neutrino density 1 times 10 to the negative 9, 1 times 10 to the negative 7, 1 times 10 to the negative 5 per cubic megaparsec. And timescales are 100, 10,000, and a million seconds. Evolution types are either no evolution or we choose MD 2014 star formation rate. It's just a type of star formation in the cosmic scale. So there are in total 3 times 3 times 2 equals 18 combinations of the settings, right? After I have each configurations, I need to compare the neutrino flux to something called 5 sigma discovery potential plot that a grad student in our team has. The method is to use the potential plot. The method is to use this FIRESONG software to produce a list of neutrino sources that is above the 5 sigma discovery potential. This red picture shows you what I've got so far. Notice that only one of the 18 configuration plots that I make is just one of them. And each time there are also natural fluctuations of the neutrino sources generators. This plot's x-axis is the sign declination or the location of the northern sky from 0 to 90 degrees. And the y-axis is sort of complicated, but you can think about it as the neutrino flux. This red line is called the spline for the 5 sigma discovery potential, and you can think of it as the cutoff line for neutrino sources. So neutrino sources above the spline have a higher chance to be found as neutrino sources since they are corresponding to higher neutrino flux, which I mark them as orange. So those are above this line, which can survive as neutrino sources candidates. So some ongoing and future works. I'm troubleshooting some FIRESONG code and also using the PACE cluster at Georgia Tech. So my next step is to combine the results of my configuration and find out the probability of neutrino sources which are above the 5 sigma discovery potential. And in the near future, very soon, we can use this simulation code to test the potential neutrino sources. Thank you so much, and special thanks for my mentor, Chris Tom, and PI, Dr. Ignacio Taboada, and other graduate students from this team. And also thank you for the funding from the STEM Scholar program at Agnes Scott College. Here are the references. Thank you so much. And here's a fun group photo for my team.